Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 40, we will cover nested logit model. So, the different concepts that would be covered would be on independence of irrelevant alternatives, IIA property of the MNL model, which we have already discussed earlier. Then we look into the nested logit model, the log sum parameter, and the complex nested logit structures that is possible in a nested logit model. So, when we have discussed the MNL model, we have discussed two properties. One is the equivalent difference property and the independent of irrelevant alternative property. Both the properties are very important and they gives MNL the strength as well as also give it certain weaknesses. So, first we will talk about one of these weaknesses in the IIA property. So, the IIA property states that for a particular decision maker, the ratio of probabilities of choosing two alternatives does not depend on the presence of any other alternative. So, that means probability of choosing A over B will not change based on whether a third alternative is present or not. But while this actually helps us to estimate the model and it also is beneficial, like when we have taken the difference of two alternatives, the third alternative did not play a role. So, it was easy to do those estimates, like we take one, we predict the probability of one mode in reference to another. But at the same time, this also creates certain problems. For example, one of these the other alternatives may not be relevant to the ratio of probabilities between a pair of alternatives. This is supposed to be, but in actual situation this results in some erroneous prediction of choice probabilities, but in some cases, not in all cases, but in some cases. Now, one famous way to explain or famous paradox is called the red bus and blue bus paradox. It actually explains this particular problem. So, let us assume two alternatives which are available. One is car and a bus, and the bus is specifically blue line bus. So, it is just a name that is given to this particular bus line. So, when we through the logic in the MNL model, we can get the probability of car estimated as e to the power utility of car divided by e to the power utility of car plus e to the power utility of blue line bus. So, it is given as 2/3, whereas for the blue line bus it is given as 1/3. So, basically the division between these two modes is 2/3 and 1/3. Now, another bus line service started, which we call the red line, which has got the same exact attributes and operating service characteristics. This means in most cases the reasonable assumption is that bus commuters will split into two lines or routes as per the following choice probability, which is for car it should be 2/3, and then within blue line bus it becomes half, 1/6, and then red line bus it becomes 1/6, because together bus was 1/3. So, when we divide it into two parts, that is blue line bus and red line bus, each because both the services are exactly same service. So, people will either choose blue bus or red bus in 50-50 percentage. So, that is why it becomes 1/6, 1/6. So, this is the expected probability that will happen. But actually if I follow the IIA property, then what happens? MNL model will maintain the choice probabilities between car and bus, blue line bus, and also between blue line bus and red line bus. So, when we talk about car and blue line bus, the probability was 2/3 by 1/3, which is 2 by 1 or 2. And when we are talking about blue line bus and red line bus, it is definitely 1, because they are both the same. So, if I take this as the base to estimate the probabilities of my three options, so probability of car becomes half, probability of blue line bus becomes 1/4, and probability of red line bus becomes 1/4, which is a mistake. So, that you can understand that we are unnecessarily reduce the probability of car is getting reduced from 2/3 to half. Why this is happening? Because we are assuming the assumption that errors or the unobserved effect, that is the E term, are independently and identically distributed, which is for all the different modes, and this is the result of this particular problem. But actually it is not in the same way, it is not independently and identically distributed. This is unrealistic because car does not share much of its intrinsic properties with both buses, and hence unobserved effects are not identically distributed. So, because car is totally separate from buses, even within buses the errors may be similarly identically distributed, but for car it is definitely different. So, what it means, if you remember from our previous lecture, if we have two separate kinds of mode or two separate variances or two different error terms, we need to introduce a scale parameter to take care of that difference. That means, when we estimate them in using a same platform, then we have to introduce a scale parameter because of this different variance in these two terms. So, in the same way, that means the buses has to have a different variance compared to the car. So, that means if I can put the buses in a smaller basket and give them one variance, whereas we can give another variance to the car, then definitely we will be able to solve the problem. So, that means there are two things coming out. One is we have to use a scale parameter, and the second thing is we have to put those identical alternatives in a group, so that we use the same parameter for those particular group. So, in the nested logit model, this actually offers the solution coming out of the restrictions of this II property. This is how I was explaining the scale parameter as well as grouping them into nest. This is that solution, and alternatives which share properties only should be grouped together, and thus on unobserved effects among them would also be identically distributed, and this results in the nested structure. So, in this part we see the basic MNL model, where we have three choices: the rail, local bus and car. And on this side what we do is we have the car which remains as it is. Instead of bus and rail, we put them in a group which is called composite transit. Why composite transit? Because it is a composite group of rail and bus which are both transit modes. Now, rail and bus is then a part of this transit, which is part of this nest. So, the same model that we were doing during RP and SP joint estimation was, we were using a nest, but it was a dummy nest. That means it was a composite nest including only one alternative. So, we were fooling the estimator by saying that it is a nest. So, there has to be a theta for that, a scale parameter for that, but at the same time there is only one alternative in that nest. So, that was this is the explanation for why we are using a nested logit structure to estimate a joint RPSP model. But in any way, so over here we create this nest. Now, one thing that you have to remember when we are creating this kind of nesting structure, this composite transit variables, or rather the parameters which are used to develop the utility equations for composite transit, they should only include the modal alternatives or the modal characteristics of transit which are common to both rail and bus. Whereas, the parameters which are different between rail and bus should be kept at the nested, we should be evaluated at the within the nested logit model. That means, within this particular nest we will evaluate those parameters, whereas over here we will take the parameters or select the parameters which are common between rail and local bus, like in vehicle travel time and out of vehicle travel time. That in both cases there is an out of vehicle travel time and in vehicle travel time. The way people value those travel time would be mostly similar, whereas the in vehicle travel time by car would be different. So, that is way in this we can bring those parameters which are mode specific, not only mode specific, but also the ones which are common between these two modes. Whereas, over here we can bring in both the mode specific parameters which are different among these two modes, plus other individual characteristics and also could be considered over here. So, over here we can see that in a nested logit structure, the MNL model assumes this form, where probability of car is exponential e to the power utility of car divided by e to the power utility of transit and utility of car. So, this is the composite transit. So, we have to create a data set out of the overall data set using only the transit characteristics, and that variable should be used to form this utility equation. And this composite transit utility is a function of both UB and UR, bus and rail, and here PT is equal to, as we have seen, the same format is also used to estimate this probability of transit. Now, once we have done that, next we determine the probability of bus given the decision to travel by transit. So, there exponential of UB divided by exponential of UB plus exponential UR, this is the second level multinomial logit model, or in this case binary logit model, that we need to estimate for this bus and rail, and provide given that the decision is to travel by transit. So, this we now need to just select the data which is specific to bus and specific to, or the parameters which are specific to bus, attributes which are specific to bus and specific to rail. We will take those attributes and then use those data to form our model and or to estimate the coefficient for this particular model. Now, characteristics which are not common are selected, that is access time may be same for both the modes and all. So, so different things which are different, which is selected in this when we are developing this particular model. And once we have got the values for this, then unconditional probability of, so this is conditional probability, this is conditional to choosing transit, this is the probability. So, the unconditional probability is probability of bus is probability of B given T into probability of T, which is the standard formula, and probability of R is probability of R given T, R given T is R given the decision to travel by transit into probability of transit. So, we multiply the probabilities with the probability of transit that we estimated in the earlier step. And so, this is probability of bus, this is unconditional probability of rail, and unconditional probability of car was already obtained earlier. So, when we add these three up, it will be 1. So, how do we now estimate this probability of transit? Because that is something which is new. We can estimate this too, as well as probability of car and transit we were doing. There the main thing is how do we form the utility equation for transit. So, characteristics of all transit submodes which are common for all nest members, that is bus and rail, plus the expected maximum utility EMU of the lower nest options. So, this is the formula for forming the utility equation of the composite transit. So, here we take the parameters or the characteristics of all transit, the attributes of all transit submodes which are common for all nest members. So, these are the common attributes that we are considering, plus we need to also include the uncommon attributes. So, we take maximum expected utility of the lower nest options, which are basically the uncommon transit attributes and of course, their utility. So, EMU is actually estimated using the log sum variable, or which is the natural log of the denominator of the MNL model, into a calibration coefficient, which is nothing but that scale parameter. So, here this log sum is log of exponential UB plus exponential UR. So, this is basically the lower part of the or the denominator of the lower nest model, this into the log of it. So, that is why it is called a log sum, and then the transit utility equation becomes log sum into this scale parameter or coefficient, you can call it is sorry not as I am wrong. This is the coefficient for this particular log sum parameter, and then we also have AT plus AN into XN. So, these are the different attributes which are common characteristics of the transit mode. So, this is together forms the utility equation for the transit. So, a transit we could have done we could have ignored this log sum, but in that case we would have lost all the uncommon characteristics of the different submodes. So, that is why that is also included in form of this log sum, and similar to a n x n, all this coefficients that we are estimating, we also need to estimate the coefficient for the log sum, and this is called the log sum parameter. So, this coefficient of log sum is the log sum parameter, and this value has to be estimated, and this is also known as the dissimilarity parameter or the nesting coefficient. And this parameter this parameter is something which is very interesting, because this parameter provides lot of information on not only the effect of that particular log sum variable, but also the nesting structure and its appropriateness. That means, the degree of substitutability between alternatives in a nest, that could be estimated using this particular parameter, and underlying correlation between the unobserved components for pairs of alternatives in the nest also could be looked at using this particular parameter. So, because it is a coefficient for a particular variable, for this particular log sum variable, the value of the log sum parameter is bounded by 0 to 1 to ensure consistency with random utility maximization principles. All beta coefficients are in that is within 0 to 1, and two things we need to understand. If this parameter is equal to 0, that means all submodes are perfect substitutes of each other, and choice of transit and car is not affected by the choice of rail or bus. That means, the model becomes it means that that means we can independently estimate the transit variable, the composite transit utility, without even considering the utility of the subnest, and that means the subnest value is of no importance. That means, that there is no effect of change within the subnest on the upper level choices. So, that is what it talks about, and whereas if it is theta is equal to 1, that means this 1 implies IA property holds, and there is 0 correlation among the modes in the nest, and the NL model, nested logit model, collapses to become MNL model. So, that means, if theta value is equal to 1, that means all the modes are having the same importance. We can assume that the IIA property holds true, and then choice between these two modes does not affect the other mode, in that it's not a perfect substitute of each other. So, it will actually be like they will help in maintaining the IA property, and it is just the opposite of when it is theta is equal to 0, and when usually theta is within 0 to 1, and that actually gives us that there is some effect of those groups or the nest on the actual mode choice, and when theta is greater than 1 and theta is lesser than 0, these are not acceptable, and this is inconsistent with the theoretical derivation. So, this is how we can interpret this scale parameter that we are using, this log sum parameter that we are using, and what it means is, based on the value of the log sum parameter, we can actually decide if we are going to use a MNL model or a nested logit model. So, we will use a nested logit model, as we have seen in the red bus blue bus paradox, that whenever we are introducing a mode within which is almost similar to another mode, it probably will not affect the other mode, unlike the IIA property where it was affecting the mode. So, if the theta parameter or the log sum parameter is equal to 1, that means it implies that it will affect the other modes in the same exact way, in the same proportion, and so there is no need for developing a NL model. So, let us look at an example. In a city's corridor, the following utilities were calculated for car, bus and rail, where utility of car is minus 0.31, utility of bus is minus 1.01 and utility of rail is minus 0.8. And overall transit, that is rail and bus utility, was estimated to be ut is equal to AT plus the log sum parameter into log sum. So, this theta and log, this is the same way that we have just explained, only AT is the bias, plus we have not taken any other variable in this particular equation, where AT is equal to minus 0.4 and this log sum parameter is given as 0.2. Now, if bus utility is changed due to city level policy by minus 0.4 determine the change in the modal share. So, that means because we are doing a nested logit model over here, we have used a nested logit model, we have this log sum composite utility. That means it will affect the other only the nested modes in a more higher way compared to the mode which is at a upper level at the upper level. But if it was not, then it would have affected it much higher. So, here we estimate this particular values, like for example, for bus we have a utility of minus 1.01 and for rail we have a utility of minus 0.8, and this is the e to the power utility, which is exponential of utility, which gives us 0.36 and 0.44. This is the total the sum of the utilities of these two particular modes, which is 0.81. So, probability of transit is probability of bus is basically bus divided by the sum of both bus and rail, which gives us 0.44 and 0.55, and this total is equal to 1. So, this is where we say that we are estimating the probability of the lower level nest given it is part of transit. Next, the transit value then becomes minus 0.41, the composite transit utility as per this particular formula. AT is equal to minus 4, minus 4.1 plus this theta parameter, scale parameter, log sum scale parameter, then 0.2 into log of this variable. So, this particular summation of these two utilities. So, this is the log sum and this is the log sum parameter, and we get a value of minus 0.45127. So, that means now we are estimating the modal choice between car and transit. So, we have the utilities of 0.31 that is already given. We have estimated the utility of transit over here, and we same way we can estimate the probability of car and probability of transit, and together it is 1. So, probability of bus is bus given transit into probability of transit, which is 0.208. Probability of rail is probability of rail given transit into probability of transit, which is 0.256, and probability of car is 0.535. Together all of them is equal to 1. And if I take the probability of car by probability of rail, this is comes to around 2.085, and probability of car by probability of bus, this is 2.57. So, now I change now the city has done something, so that the utility of bus has become minus 1.41. So, rail remains as minus 0.8. So, we can estimate again between bus and rail, the probability becomes 0.35 and 0.64, and this transit could be estimated in the same way, where the composite utility is 0.483. Car and transit could be again estimated in the same way, where we get a probability of 0.54 and 0.456, and then probability of bus, again probability of bus given transit into probability of transit equal to 0.16, and probability of rail given transit is 0.29. So, we can see there is reduction in bus because the utility have reduced. So, and most of the utility that was reduced is gained by the rail, and very little effect has come on car, because last time the car was something around 0.535 and now it is 0.54, whereas rail was 0.256, whereas now it is 295. So, rail has gained much more. So, we can see the same values. Probability of car by probability of rail is now 1.83, and probability of car by probability of bus is 3.37. So, we can see that the ratios are not maintained, unlike the IIA property, where it was supposed to be same. If it was MNL model, then we would have got the same ratios over here. So, this shows that change in the utility of bus did not affect the other two modes proportionately. If theta value, but however, if the scale parameter is 1, you can just substitute these values with 1. I have already done that. So, but I have not shown it here, but if you substitute by 1, then the change would have been proportionally same. So, if you, as we have discussed, then when the theta value assumes 1, then it becomes almost the nested logit model becomes a MNL model, and you will see that then the change would be exactly having the same proportions. So, this we can also call as the sequential estimation method. So, this means we are sequentially estimating first between bus and rail, then estimating the transit probability, and then estimating using this particular way we are doing car and transit, and then determining the probabilities of bus, rail and car. So, this transit utility, if I have estimated this based on the actual data set, I would have defined the utilities and all, and we could have defined the utility equation and then have done this estimate, then this is called the sequential estimation method. But usually in most of the softwares, or when we solve this kind of nested logit model, we adopt not a sequential approach, we adopt a simultaneous approach, and for that we have to do take some considerations. So, let us take this particular example. We have the upper level choice, and this we have got drive alone, shared ride, and then we have public transit, within which there is bus and light rail. So, that means this is the upper level choices between drive alone, shared ride and public transit, and that within the public transit there is two alternatives, which is bus and light rail. So, we call the upper level the marginal choice among drive alone, shared ride and public transit, and the lower level we call it conditional choice, because it is conditional upon being within public transit. Now, sometimes we may feel that this nested structure that we are using to derive this kind of models, this is related with the way individuals makes a decision. That means, individuals also think, okay, should I take public transit or drive alone, or then they decide between public transit and then between bus and light rail. So, this is what we are, this may feel like that, but actually no. When people are evaluating, they may probably evaluating between all the different choices that are eventually available. This structure is given just to facilitate the way we do the estimates. It has got nothing to do the way how the behavior of a people actually is defined. So, that we should keep in mind. So, conditional choice probabilities could be derived for bus and light rail, as we done in the earlier slides. We have shown the bus and light rail. It was we have shown the formula. Only difference with that particular formula is we introduce a parameter which is, we can call it a scale parameter, which is theta pt in all the utility equations. Now, if I do that, I also know that because of this MNL properties, this has got no effect. So, introducing we can introduce any scale parameter, it actually cancels each other out. So, that is not a problem at all. So, this standard logit form is modified with a log sum parameter in the denominator of each utility function. So, that means we are introducing the log sum parameter that we have defined earlier. For that matters, here you may also call it just as a scale parameter. So, we are introducing this particular parameter in the denominator of all the utility functions. That is all, and that will not change the outcome of my probability. So, this is something which we are doing to facilitate my simultaneous estimation procedure. Then the marginal probabilities for dA becomes exponential of VDA divided by exponential of VDA drive alone plus exponential of shared ride plus exponential of the composite transit utility. What is composite transit utility? Composite transit utility is basically the utility of some of the common characteristics of the public transit modes VPT plus the log sum parameter into the summation of all the, or the log of the summation of all the probabilities of the alternatives which are in the nest. So, this is given by tau pt, which is log of summation of all the exponential V bus by theta pt, which we have introduced earlier, and then exponential of V of light rail divided by this log sum parameter or any scale parameter that we have said. So, this form actually, and then we have this parameter over here as well, which is the log sum parameter. So, if I write my probability equations in this particular form, where VSR, and then we are also finding exponential, we are determining composite transit probability in the same way. So, we are bringing this form over here for this is the composite utility of transit, which we have learned that it is composed of the log sum parameter into the log sum variable plus the characteristics of transit. So, that is what is given over here. So, if the data is in this form, so we can now form the log likelihood functions, which could be also we can find the derivative of this function and equate it to 0, the way earlier that estimates have been done by other softwares by simulation and all, and there we can find at what should be the values of those parameters, both the beta coefficient, all the coefficients of all the attributes plus the scale parameter would be also evaluated in the same way. So, this scale parameter value we will be able to get, and then using that scale parameter we can easily form the probability utility equations of the different utility equations for the different modes, and we can determine probability of each particular mode. So, all utility function parameters beta within the nest are scaled by theta, which is the log sum parameter, and then since this theta is bounded by 0 and 1, as you can understand, the choice between nested alternative is more sensitive to changes in variables in these functions than the alternatives not in the nest. That you can understand. If I am dividing over here by theta pt, the effect it will have is much more than it is over here. So, over there it is directly affecting the utilities of the mode. So, the effect would be of this particular parameter would be higher over there. So, we use simultaneous equation estimation method to do the estimates, same as the MNL model that has been estimated. A single maximum likelihood function is formulated and maximized, and we can use software like logit, which can estimate NL models, and similarly Python BiGeom can also be used to estimate NL models. We have already discussed Python BiGeom in the last lecture, and you can go to this particular example which is given in the EPFL website using a data set from Swiss Metro, where they have used a nested logit model. You will see the example is almost similar to what I have shown in the last example of Python BiGeom. Only thing, they have also introduced the nesting structure within that particular code. So, the code is given over here. You can just go to that website and can check the code. And finally, I would conclude by saying that this nesting structure is very, very important in overall land use transportation modeling, because we have been talking about joint modeling for quite some time now. So, we have talked about combined trip generation, time of the day, destination and mode choice models. So, that means there could be a combination of destination and mode choice, there could be a combination of time of the day and destination choice. So, there could be different combination models, and we can see over in the slide, we can see in this slide that we have a choice, then we can either take a trip or a no trip, and then we have got this AM peak, off peak and PM peak. These are the 3 time periods. This is the time of the day model, and for each time period we can have different options of destination, and within each destination we have got different mode options. So, that means for a particular destination we will choose we will only have certain alternatives available to us, and accordingly we will choose a mode, and then within a peak period we will only choose during that particular time certain destinations are only available, we will choose that destination. So, we can create this kind of complicated nesting structures, and we can develop joint models. It could be either of location choice and mobility choices like residential location choice model, or it could be something related with destination choice model, it could be something related with joint mode choice and destination choice model, and so on. So, this kind of complex nesting structures could be also explored using the same principles that we have discussed. So, this is how we can solve a nested logit model. So, these are the references that you can consult. And finally, to conclude, nested logit model offers a way to go around the restrictions arising out of the II property. Calibration coefficient of the log sum needs to be estimated. The nested logit models could be estimated both sequentially and simultaneously. and nested logit models can be used to develop complex joint models, and that actually gives the strength to this discrete choice approach. Thank you.